Well, thanks very much for the invitation. I'm delighted to be here. Okay, so this is intended to be a colloquium talk, so that means that certain people will find that I've insulted their intelligence. I apologize in advance, but people who have questions should feel free to ask the questions because it's a colloquium talk. Okay, billiards are often introduced in dynamical systems as kind of toy models representing certain types of behavior. Because it's something that you can write down explicitly, and a lot of times in dynamical systems, the things you actually want to deal with are rather technical, and billiards is concrete and kind of pictorial. For example, certain billiard tables are used to represent chaotic behavior. Other billiard, for example, convex scatterers. Other billiard tables, for example, the ellipse, are used to represent regular behavior, non-chaotic behavior. I want to consider a class of tables called rational polygonal billiards. And I'm interested in representing somehow the transition between regular and chaotic behavior, in the sense of I want to give a kind of a toy model for something that's neither regular nor chaotic, but just on the boundary of both. Okay, so here are some examples. So I'm looking at polygons in the plane, and I want the angles of my polygons to be rational multiples of pi. Here's a fairly classical billiard table. Then a somewhat less classical billiard table would be this one. And maybe even more exotic would be something like this, with a barrier part way down the middle. And then I'm interested in the behavior of billiard trajectories in these tables. So those would be paths traveling at constant speed, so that the angle of incidence is equal to the angle of reflection. Or here we might have something that bounces off the barrier at one point and then goes to the other side, something like that. Okay, so the condition that my angles are rational multiples of pi, it's an important condition. So in general, you might think of this billiard flow as taking place in some kind of three-dimensional phase space where we have, since the direction is fixed, we've got an angle. I mean, since the speed is fixed, we have an angle and a position, so three parameters. But with this condition that the angles are rational multiples of pi, you can really think of these billiard flows as taking place on surfaces inside these three-dimensional loci. So you sort of have an invariant of motion in the sense of physicists. One way to see those surfaces is by unfolding the table. So if we take the square here and unfold it, we get a in doing this unfolding procedure, we're taking our billiard trajectories. We can think of this as taking our billiard trajectories and straightening them out so they become straight lines. And we can think, in this case, of our billiard flow is a straight line flow on the torus. So here we have the flat torus, and we're looking at the straight line flow. So that would be case 1. In case 2, again, we can do an unfolding construction. So we start with this isosceles triangle, and we can unfold it to get an octagon, regular octagon. Okay, and in this case, we would have an identification of sides in the following way. And this identification of sides induces a certain identification of the vertices. So in this case, all of these vertices get identified. The cone angle at each vertex is 3 pi over 4. So what we produce in this case is a surface of genus 2, which you can check with a flat metric on it and a singular point. And at that singular point, we have a cone angle of 6 pi. All right, so you could think, if you want to think about that geometrically, you can think about gluing together these little sectors here. So what you get is something that looks like a sort of a branch cover, threefold branch cover over the disk at a single branch point. Right? You've kind of sort of glued 3 disks together by making little slits in them, and so you might think of it something like that. So these are, let's see, and in this remaining example, we get a surface of, this unfolds to give a surface of genus 2 with 2 4 pi cone angle singularities. Okay, so these, so we're getting flat surface with cone type singular points. These surfaces arise naturally in the study of Riemann surfaces. This is one of the types of metrics that's natural to consider when you're looking at a certain conformal structure on a surface. Hyperbolic metrics are another type that's natural, but in many cases, this is the type of metric that you really want to be looking at. This arises a lot in algebraic geometry situations, for example. Okay, so I want to introduce techniques for studying polygonal billiards. And I want to do that by looking at a sort of a sample problem and then introducing techniques to address this sample problem. And the sample problem is the following. So if we're in the, say, the classical situation of the billiards, then as you probably know, in a serious billiards game, you don't just hit the ball and see what goes in. You have to call your shot. So you have to describe the path that your shot will take. So I'm interested in the question of, well, what are the possible paths that billiard trajectories can take inside this surface, or inside this, this square? So if we were to, for example, label the sides, then given any trajectory, we we get some sequence of labels. And the question is which sequences of labels arise. Okay, so this is important if you're, again, if you're playing serious billiards and you're betting, say, on whether somebody can make the shot they've called or not, then it's important to recognize when they've called a legal sequence, a legal shot, right? A legal sequence of sides. If, for example, they've called a shot which cannot be obtained, this is a good point at which to increase your bet. Okay, so it's I'm trying to give you some useful tools here, not just in a mathematical world. Okay, so it's a practical problem from that point of view. Okay, so let me simplify the problem a little bit. We can look at a simplified labeling system. If I let me just label the top and the bottom with an A, and the left and the right with a B. Okay, now if you know a sequence of A's and B's, you can recover a sequence of small letters, right? Because between, the first B will hit one of these sides, but the second B will hit the opposite side, right? So you can determine which B's get replaced by little d's and which get replaced by little b's. But if you know which side is hit initially, but in fact, so if you can describe sequence of capital letters here, you can also describe sequences of little letters, right? Okay, now here's the other observation. I want to sort of turn our question about the billiard table into a question about the torus. Well, if you've got a, so variation here, which sequence of A's and B's arise. Now, if you've notice with this sequence of A's and B's, it's invariant under the two kinds of flips. You can, a horizontal flip or a vertical flip. It doesn't change the sequence. So say if you've got, let's look at a trajectory here that starts off like this and then reflects over here. Well, let's apply this vertical flip to this trajectory. Then we get a trajectory which is parallel to the initial one, but just coming out of the point that this one went in. So it's as if now we have a trajectory on the torus, right? Instead of one on the billiard table. Okay. So and then the same thing happens when we go up to the top. We can either continue it this way, or we can flip it. So it comes on, comes down to the bottom, right? So we can think about our trajectory as taking place on a torus instead of on the original table. Okay, and we can also, so we may assume that the direction of our trajectory is in the first quadrant. Is in the first quadrant. Okay. Now let me observe that there's we can see immediately a certain restriction on the possible sequences. If we have a trajectory, if at some point in our sequence we see two B's in a row, well, we know our trajectory is, subsequent pieces of the trajectory have exactly the same angle. So we can see that in the future, we might get a B and an A. We might get two B's again. We might get an A and a B, but we'll never get an A and an A, right? So if at some point we see two B's, we never see two A's, okay? So we could think of our trajectory as being described, such a trajectory as being described by a transition diagram where we're allowed to have two B's. B can follow B, B can follow A can follow B, but we're not allowed to have two A's. Okay, let's call this diagram 0. Similarly, the other possibility is that our transition diagram is of the opposite type. We can have two A's if the slope is bigger than 1, but we'll never have two B's. Let's call this diagram 1. So let's say that a sequence is admissible if it is compatible with 0 or diagram 0 or 1. Okay. Now, okay, so that gives some simple-minded conditions that have to be satisfied. But there are some more subtle conditions that have to be satisfied as well. So let's consider a sequence of type 0 here. And so the trajectory looks something like this. And say the original sequence sigma is something, and then A, B, 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 A, B, B, A, and then something else. So labeling here A, B, B. Let me add an edge to the table and get a kind of refined, yeah, question?
What if we never have BB or AA? Or it's impossible?
What, then what happens?
Is that sequence possible?
Yes, yes, yes. Well, what if you never have, I mean, you have BB if the slope is less than 1. You have AA if the slope is bigger than 1. If you never have AA or BB, the slope is 1. Right? So that is a possible situation. It's actually compatible with both diagrams, right? So it's kind of a boundary situation, but that definitely can happen. Okay, so I want to add an edge here. It's not strikingly different. It's color. Let me see. Call that C. Maybe it's better to, let's see. Maybe it's better if it's yellow. Okay. So I can look at my coding instead with respect to the 3 letters instead of the 2 letters, right? So what do I get here? I get an A, I get a B, and if I go from B to B, I really have to have a C in there. And again, going from B to B, I have to have a C. And then I get an A, and then a B, then a C, then a B, then an A. So I can deduce the 3-letter coding from the 2-letter coding, right? It's automatic, okay? Now, let me make a geometric transformation of the table. Okay, I want to do a shearing on the table. So if I do that, then let's undo a shearing so that C becomes vertical. Then A sort of extends over to the right. B extends to the left. Oh, I'm sorry. A is up here. B is here and here. Maybe this is a little low. B is here and here. And when I do this shearing, notice that my trajectory is taken to a new trajectory. Right? The shearing is a linear map, so it preserves straight lines. So I've got my new trajectory. No, I'm sorry. Yeah. So I've got a new trajectory here. And if I call this, let me use the same letter sigma for my original trajectory. And then this new trajectory, I've got sigma prime. Notice that sigma prime, while I've preserved lines, I have not preserved distances. Sigma prime is traveling at a different speed than sigma. It's traveling slower than sigma was. Okay, now let me do a certain transformation of this picture here. So I can cut along the edge C and translate that over to there. Now I have now C is on the side here. A is at the top, and my B is running through the diagonal. Okay, and here's I've got my new trajectory sigma prime. Now notice that I've got another trajectory in the table, right? This is whatever, so I have a new trajectory, and I could calculate its cutting sequence with respect to the new square, right? In order to do that, what happens, so if I go from here to here, I drop the B, and so I want to go from there back to the original coded table. So this, and I want to just turn my C's into B's. Drop B, turn C into B. Okay, so that gives me a new sequence here. Gives me a new sequence where I, first of all, drop the B's. So I get A, C, B, C, A, B, A. Well, I'm sorry. So what am I doing here? First of all, I drop the B's. So I get A, C, C, A, C, A. Okay, so I drop the B's, and now I turn the C's into B's. I get a sequence A, B, B, A, B, A. Right? So this is the actual sequence corresponding to this new trajectory sigma prime. Hence this new sequence, which I've attained by the old sequence by some process, some transformation here, some symbolic transformation, will again be admissible. It will again be correspond to a billiard path. Okay? So I have a sort of a purely combinatorial operation that I can do on sequences, and I know that once I've done this combinatorial operation, again I will get an admissible sequence of symbols. So let me summarize. The definition a sequence is characteristic. Oh, so let me call this operation here So the operation that takes sigma to sigma prime, let me call this derivation. Sequence is characteristic if it is admissible and the result of doing any number of derivations is still admissible. Okay, so clearly a hitting sequence for a billiard trajectory is characteristic. Because every time we do this operation, we're staying in the world of hitting sequences of billiard trajectories. And let's say, okay, let me do an example here. Okay, so let's say sigma equals A, B, 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 A, B, B, A, B, 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 A, B, B, A, B, B, A, B, 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 A. Okay, and then sigma prime. Well, we've seen what the effect is of applying sigma prime. This is going to drop one B from each group, right? So we get A, B, B, A, B, A, B, B, A, B, A, B, A, B, B, A. And if we derive again, as we know we can, we get A, B, A, we dropped out the B, A, B, A, dropped out the B, B, A. Okay, so the conclusion is that sigma double prime needs to still be admissible, right? So that says that, let's see, so yes, so that tells, so that tells us, let's see, what does that tell us? That tells us that so we know in sigma double prime we're seeing pairs of A's together, so we can never see pairs of B's together, right? So what does that tell us? It tells us in our initial groupings of B's, the numbers of B's can differ by at most one, right? So we see 3, 2, 3, 2, 2, 3. Right? If we saw 4 B's at this initial stage, then we would get down to a non-admissible sequence at this stage, right? Because we would have both pairs of A's and pairs of B's. Okay? There's something else that's going on here. If we if we derive one more time, sigma. Okay, now here we've got, say, a B, an A, an A, and a B. Let's see. So B, 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 B. So 2, 1, 2, 1, 1, 2. So here we have let's see, double prime. Okay, I'm sorry. Let's derive one more time. So we have the A, B, A, B, A. Okay, for some reason this A, B, A, B, A.
There should be another A in the last group of A's.
Okay, so in the last, in this one?
Yeah.
Thank you. A, B, A. We derive one more time. We get, let me just copy down what I've got here. A, B, A, B, A, B. So if we derive 3 times, then we get a sequence of A's and B's where the sequence that we get just comes from these numbers, 3's and 2's, right? We've taken each 3 and replaced it by an A and each 2 and replaced it by a B. So somehow the structure, the longer scale structure of our sequence is reproduced by this in this shorter sequence, right? We've got a we have a is that correct? If I
start with an
when we get down here,
you're driving with respect to A, so the A should
Yeah.
okay. Yeah, so we got 3, yeah, okay. So the B's correspond to the 3's and the A's correspond to the 2's. Okay, so the deal here is that our initial sequence we've got in our B's, there's groups of 2 sizes, and those 2 sizes are just determined by this sequence of A's and B's. So the sequence of sizes has to be admissible in this sense, right? This has to be an admissible sequence, okay? So we're seeing this way, we're getting infinitely many conditions on the sequence. If our initial, and they're getting more subtle as we go along. If our initial sequence had 2 B's here to start with, then we would get 3 A's down there and we would get a contradiction, right? So if the initial sequence, I mean, it somehow, at this point we double the bet, right? I mean, if the initial, okay. But somehow we're getting a sort of more and more complicated condition on our sequence, which is propagating, right? Where the influence is spreading further and further. Okay. Right, and then so a hitting sequence from a billiard trajectory is characteristic, and the converse is essentially true as well. A characteristic sequence is a hitting sequence of a billiard. So we can use this technique. In fact, I mean, we can use this technique to detect fake cutting sequences. So this technique does detect fake cutting sequences, or hitting sequences, I mean. Okay, so the some of you may have noticed that this analysis that I'm giving is not completely new. This, in fact, this kind of analysis of possible trajectories, so it dates back to, so this analysis dates to 1896. Okay, so done both by Christoffel and by Smith in about close, in papers that appeared close to the same time. Let me mention similar analysis can be done for the octagon. And this dates to, so this dates to 2015. Okay, so it can be done for the octagon, but it's not a general, it's not something that can in general be done for all billiard tables. Let me give you a more geometric picture of what we're doing, a more global picture of what we're doing. If we think about the space of metrics on the torus, okay, so when we do this operation, we can think about changing, using our shear to change the metric on the torus, right? We're constructing a conjugacy from a billiard flow in one direction to a billiard flow in a new direction. So the space of metrics on the torus can be described by this picture, which came up in Karen's talk as well. So we can think of the space of, we can identify the space of metrics on the torus with the points in the Poincare disk. Okay, so this is a familiar, perhaps done more familiarly, identifying the space of metrics on the torus with the upper half plane. And there we can describe a fundamental domain, but I want to think about this in the disk picture. Okay, Karen drew this picture and everybody seemed to be happy, so I'm trusting that you're equally happy when I draw this this picture. Okay, so what are we doing here? Oh, so we can think about this as the space of metrics on the disk, right? These are sort of naturally related to the fundamental domains. And indeed, for a particular, if we have a particular torus and we want to choose a particular direction, we can associate that with a unit tangent vector on the disk. So we can think of our initial torus as corresponding to
I'm just a bit confused why on the right it's not touching the line, the half strip with the circles.
This one? Yeah, so there's a circle that does indeed touch the line.
The left picture corresponds to fundamental.
There's a fundamental domain inside here. I'm not trying to explain something. I'm trying to trigger your memories. Because okay. So right. So there's this picture is maybe half of this. I'm not sure. Let's see. I'm trying to trigger my memory now. Okay.
Well, two of these pictures is that.
Yeah.
I would say no, even more. Yeah.
If you take these two and put them together in the opposite way, you get these two. Right?
Yes.
Take these, put them over like that.
Yes.
Okay, so this is the square torus, and this is the torus with the threefold symmetry here. So we can think of our operation as giving a conjugacy from one flow to a different flow, as moving inside this picture either this way with one type of either this way or this way. Right, and then so we've got a let's see, either either this way or this way. So in general, a sequence of these sort of these rescalings of transformations of type 0 or type 1 corresponds to a sequence of choices here going through these fundamental domains. Okay, so another way of describing this, an initial direction corresponds to a point on the boundary here, and we're trying to find the appropriate sequence of we're finding the appropriate sequence of fundamental domains that gives a path landing at that point. So we can think of this as a in the language of polygonal billiards, this is often described as some kind of renormalisation operator. So it's some conjugacy between two systems, which is changing the scale of the system. Okay, so in this case, the point of the conjugacy was to change the rate. What we're doing at each point is finding that conjugacy which maximally contracts the direction in which we're interested. Okay. Okay, let's see. Okay, so an interesting special case, or perhaps an interesting special case, is the path that alternates right and left at each point. Okay. Well, okay, so let's see. Right, so in the, let me just Right. So if we consider this the path that's the alternating path that goes first left, then right, then left, then right, then that lands here at the golden mean. Okay, so that corresponds to the trajectory in the direction of the golden mean. In this particular case, we can think of our rescaling operations, if we do two steps of our rescaling operations, as performing a linear automorphism of the torus, which has the golden mean direction as an eigendirection. Okay, so we're concretely rescaling this trajectory. We're concretely building some conjugacy from the torus to the torus that preserves this direction and rescales it. Okay, so in some ways, what we see in that case is trajectories that sort of reflect the same statistics when we rescale them. Okay, so I just want to make an analogy here. Right, we want to think of our billiards as a toy model for something physical. Okay, and I'd like to make a analogy with a picture in physics, which involves a transition from between states of water from liquid to gas. Okay, so this is something that's studied seriously under the language of renormalisation theory, and I don't want my comments to be interpreted in a serious fashion, but I want to say that in some respects our toy model is reproducing some features of this actual physical situation. So if we look at the state of gas, state of water as a function both of temperature and pressure, so we have there are three states, and there's a triple point. So this pressure is this line is 1 atmosphere here, and this is 0 degrees centigrade and 100 degrees centigrade. So we have the freezing point and the boiling point. So this is ice here, this is water here, this is gas gas here. Now, if we follow, if we increase the pressure, the boiling point increases, so we can move up this line. At some point, we get to a critical value. At this critical value, we get a state which combines the features of the gas and the liquid. So this is described very poetically in an article by Ken Wilson in the Scientific American in 1979. It says, near the critical point, water develops fluctuations in density at all possible scales. The fluctuations take the form of drops of liquid thoroughly interspersed with bubbles of gas, and they're both drops and bubbles of all sizes from single molecules up to the volume of the specimen. Precisely at the critical point, the scale of the largest fluctuation becomes infinite, but the smaller fluctuations in no way diminish. Any theory that describes water near its critical point must take into account the entire spectrum of length scales. Okay, so what we're seeing is something like what we see here or what we see in this golden mean example, we're seeing a certain behavior that has a certain scale invariance. Okay, so I mean to think of this, I'm not saying anything novel about renormalization here. I mean to think of this as a toy model. And as a toy model, you think of a toy fire truck. It's interesting to make an analogy between toy fire trucks and actual fire trucks. As long as you don't try to put out fires with toy fire trucks, it's still a useful. Toy fires are fine as long as you're careful. As long as you're careful, right? Use it appropriately. But I think it's interesting to think of to make this analogy. It's not necessarily interesting for the physics, but it's interesting for the the world of polygonal billiards. Okay, now we see a certain rescaling feature going on in this example. But we don't see something that's, there's another characteristic feature of this kind of critical value behavior, which we don't see, which is universality. But there's another problem, and this is more connected to things I'm thinking about now. Another problem in billiards, where at least conjecturally we do see an element of universality. So let me tell you the problem, and I'll tell you what the connection is here. Okay, so the question is, show that the number of closed billiard trajectories of length less than L grows like constant times L squared, and compute the constant and compute C. Okay, so this is this is a question which is also connected.
For what billiard?
Pardon?
For what billiard this question?
So rational polygonal billiard. Okay, so and it's for the most part it's an open question. Okay, but I want to say that these techniques that I've been describing are useful in addressing this question. Okay, so if we go back to this picture above, then the moduli space of curves is the quotient of this picture by the action of SL2Z, so it's the space of unmarked tori. And using these renormalization ideas, a direction in which we have a closed trajectory is a direction in which the geodesic heads into the cusp region of the modular surface. So if in this picture we draw circles around of fixed size of corresponding to this cusp in the modular surface, then the collection of directions of geodesics of length L corresponds to the intersections of an appropriate circle with these cusp regions. Okay, so here I'm thinking, okay, so does that, let's see, so the, right, so instead of, right, so we could think more directly, instead of applying this sort of sequence of renormalizations, we could apply the geodesic flow here, which gives us a way, which gives us, okay. So, okay, so let me just, so what's the point here? The point here is that in order to prove this conjecture, we need to know something about how large circles distribute themselves in this moduli space, how much time they spend in the cusp. Okay, so and then we want to analyze that sort of the limiting behavior of these large circles. Now, if you take a circle in the hyperbolic plane, if you take a circle in the hyperbolic plane and you increase the radius of the circle, it converges not to a straight line as it would in the Euclidean case, but to a horocycle, right? So the understanding the behavior of large circles reduces to a question about understanding the behavior of the horocycle flow. And in this case, it's the horocycle flow on the moduli space, not of tori, but an appropriate moduli space of translation surfaces of a fixed genus and collection of cone angles. Okay, so and that's the topic which I'm currently involved in, is understanding these horocycle flows in trying to address this question. Right now it's answered in certain cases of surfaces of small genus, but the general behavior is not quite clear. Another way of describing this is, if you're familiar with Ratner theory, it's kind of analogous to trying to understand Ratner theory for strata. Ratner theory tells you something about nice behavior of group actions on homogeneous spaces, and here what we want to know about is nice behavior of appropriate group action on a stratum. And at the moment, it seems like there's it's not at all clear what the answer is. There seems to be interesting paradoxical behavior of these horocycle flows. And maybe I should stop here.
This conjecture for rational billiard or not?
Just for rational billiard. It's a conjecture for rational billiard. It's only known in certain special cases.
And well, in the rational, you cannot play this nice trick with the covering, but what is known in the rational case?
In the irrational case. In the irrational case, almost nothing. Certain very brave mathematicians have tried to attack the irrational case, we haven't heard back from them yet. It's kind of like a trip into the unknown, and they're still on the trip. But let me say that the rational case is already quite complicated. So the irrational case, you need to somehow, it's probably good to understand what works in the rational case and see how you can generalize it. And it hasn't really been done yet. Yeah.
Mariam Mirzahani is well known for her works on counting the lengths of geodesics.
Mm-hmm.
And if I remember it correctly, the lengths seem to be it's quite similar relationship with L. And is there any connection?
No. So not really. If you look at this question in a hyperbolic metric, then the lengths of trajectories grows exponentially. Mariam looked at the growth rates of simple closed curves, for example, and those grow polynomially, but it's not directly connected to the quadratic growth in this setting.
Thank you.
So, any questions? Yes.
Yeah.
Are there any results about high-dimensional cases, about, for example, billiards and cubics and?
Yes. Okay. So another natural question, and for the most part, I think there's some results, but they're very slight. So there's two possibilities. One possibility is that things get a little more rigid in higher dimensional situations. So it may be that in some ways this is the most interesting case. I don't know for sure, but there's not a very comprehensive theory. People are sort of at the stage of trying to understand certain examples. Yeah.
So, any more questions? Well, then let's thank our speaker again. Thank you.